We continue in the theme of electronic structure of atoms, and now we're going to be looking at the periodic table. So we know that atoms exist, we know that they have electrons, protons, and neutrons. We know that the different number of protons determine what element you're looking at, that there are electrons. Each element has a certain number of electrons determined by the number of protons it has, and they are structured around the nucleus in a particular way, and that's what we call the electronic configuration. So the periodic table is an attempt, the most successful attempt so far, to put all the information together in one place. So how can we make a sense of, well, at the moment we have 118 elements. In Mendeleyev's time, they knew 40 something elements, maybe 60. How do we make sense of all those elements? So he observed that elements that were listed in order of their atomic mass show repeated properties, that if you put the elements in particular, if you order them in order of increasing mass, you were able to see patterns, that elements had similar ways in which they would react with other elements. For example, the reaction with oxygen, the reaction with water, or lack of reaction with water, that sort of things. And now we know that it's not about the atomic mass, it's not how much they weigh, is the number of electrons they have and how they are distributed. But at the time, Mendeleev didn't know any of that. He published his periodic law and his periodic table in 1869, and another chemist, this one German chemist, Lothar Meyer, came up with a similar periodic table around the same time. So we use the periodic table, we chemists use the periodic table because it's a graphical display of the elements in order of not mass, because now we know that mass is a tricky thing because you have the isotopes, you have to take, which Mendeleev didn't know. This was 1869. Remember, neutrons were not discovered until 1932, so it's not about how much they weigh, it's their atomic number, the number of protons and the number of electrons they have, and they are ordered in a particular way that elements that have similar properties will fall in the same column. So this is an example of a periodic table from ptable.com. I will put the link on Blackboard, and the one online is interactive and you can click and see different things. This one is a static one. The first thing you look at in a periodic table is well, it tells you all the elements we have. At the moment, 118. It tells you, well, the name. In this case, not all of them have the name, but it tells you the symbol. Another thing that all periodic tables will give you is the atomic number. So the number of protons it has, and therefore the number of electrons is going to have in its, when the atom is not interacting with anything, in its neutral state. One thing you look at in a periodic table is the period. The period are the rows. So the rows are called periods, and you have period 1, 2, 3, etc. up to 7. And the period tells you the highest energy level occupied. So how many electrons that element is will be given by the atomic number, because the same as the number of protons, and the period number will tell you what is the highest energy level occupied. So in period 1, the highest energy level occupied will be 1. And in period 7, the highest energy level occupied will be 7. And that determines that those electrons in that energy level determines. It tells you that the electrons of that are going to be reacting will be on energy level 7 or 6 or 5 or whichever period you are looking at. Groups. Another thing that you look at in a periodic table are the groups that used to be called families. Now we kept the name group. And there are 18 groups in the periodic table. So groups are the columns. So elements in the periodic table are grouped by groups. And they used to be called families because they are a family. They share properties. And it is important that so all these, group 17 that we call halogens have similar properties. They will behave in a similar way, and yes, they will be faster or slower, and that will depend on their position depending on their period, the position in that vertical. But the fact that they belong to the same group is because they have similar properties. The same with the alkalines. Well, I will forget hydrogen. Hydrogen is very funny because it only has one proton and one neutron. So it has very strange, sometimes it behaves like it does some things and not the other. Many periodic tables will stick them in the middle. Typically it's put with group 1, although it has not many things in common with the rest of the group. So group 1, from lithium to francium, they are the alkalines. Group 2 here, head by beryllium, are the earth alkalines. And belonging to a particular group or a particular family, it means that you have similar properties to the other elements that are part of the same group. We call the elements of the groups 1 and 2 and 13 to 18 the representative elements, and the ones here in the middle are called transition elements or transition metals because they are all metals. And some of you might be familiar with calling them, they sometimes are called the D group. And they're called the D group because they are the ones in which the d orbitals are only partially filled. So when they are doing their bonds, they're going to be using those electrons from those d orbitals to expand the number of bonds they can do. And again, you might be familiar, you may or may not be familiar, but sometimes people will call these two first groups the S group, and the groups 13 to 18 the P group. And again, that refers to the electrons that those elements tend to use to form bonds. So in the case of groups 1 and 2, alkalines and earth alkalines, and our friend hydrogen, they will use s orbitals, and electrons in s orbitals, and groups 13 to 18 use p orbitals to make their bonds. Oh, and finally, you've got here the F group. And they're called the F group because their claim to fame is that is where you have F electrons in F orbitals, or F orbitals that are partially occupied. So they are not complete. So why is the periodic table useful? Well, because it's set up in such a way that the position of, if you know the position of an element in the periodic table and you know what the neighbors are, you know which period it is and what group it is, that allows you to infer how, in general trends about how it's going to behave, how big it's going to be, whether it's going to be a metal or a non-metal or a metalloid, and particular properties, ionization energy, electronic affinity, and electronegativity, that are going to tell us how good is that element at making bonds and what type of bonds is it going to make. So in the next slides, I'm going to be covering all those aspects. The first thing that you can say quickly about an element, if you know its position in the periodic table, is whether it's going to be a metal, a non-metal, or a metalloid. So a typical behavior of metals, they tend to lose electrons, they form positive ions, we call them cations. and they have the usual metallic properties. They are lustrous, they are malleable, and they are good conductors of heat and electricity. If you're in another part of the periodic table, that's where the non-metals are. And non-metals in general tend to gain electrons. Not always, but in general that's what they do. They tend to gain electrons to form negative ions. And their physical properties tend to be, well, opposite to the metal ones. They are poor conductors of heat and electricity, and they tend to be doesn't have this metallic shine that you associate with metals, and they tend to be brittle. And then you have something called metalloids, which are in the boundary between metals and non-metals, and they have properties that are intermediate between those two categories. So if we go to the periodic table, in this one, you can see the green and the mauve color represents the non-metals, and except hydrogen here in the little corner, because of that tendency that hydrogen has a tendency to lose one electron, and that's what puts them in that particular group, in group 1. But that's the only thing it does that in common with the others. In all the other properties should be better put on the right of the periodic table. So you've got all this section here, including organesson, although I've done a terrible job highlighting it, are the non-metals. Then you have all the rest of the periodic table, almost all the rest of the periodic table, all over here, and also these ones here, and those are the metals. And then you have the metalloids that are in these little, there are half dozen of them, and they are in the boundary between the metals and the non-metals.